Imagine a world where your morning coffee is brewed by a robot barista that anticipates your caffeine needs based on your sleep data from the previous night, where your commute adjusts in real time to avoid traffic jams predicted by city-wide sensor networks, and where your healthcare is personalized through continuous monitoring by wearable devices that communicate directly with your doctor. This isn't science fiction, it's the burgeoning reality of cyber-physical systems, or CPS, and data integration. These technologies are rapidly converging the cyber and physical worlds, promising to reshape our lifestyles in profound ways. In this video, we're going to explore 20 key concepts driving this transformation, each playing a critical role in revolutionizing industries and enhancing our daily lives. From edge computing that brings processing power closer to the source of data, to digital twins that mirror physical assets in the digital realm, and artificial intelligence-driven predictive maintenance that keeps our systems running smoothly, we'll uncover the building blocks of this interconnected future. We'll also delve into the challenges, especially around security and ethical considerations, that come with integrating these advanced technologies. So, whether you're a tech enthusiast, a business leader, or simply curious about what the future holds, join us as we unpack the transformative potential and the complex challenges of cyber-physical systems and data integration. First up, we'll explore how edge computing is fundamentally changing the way CPS operates. The first concept involves edge computing in cyber-physical systems, a crucial innovation that's reshaping how we interact with data in real time. Edge computing essentially brings data processing closer to the devices where the data is collected, rather than relying on a centralized cloud server. This proximity is particularly significant for cyber-physical systems because it dramatically reduces latency, the delay between a command and a response, which is critical for real-time applications. Think about autonomous vehicles. These vehicles generate massive amounts of data from sensors, cameras, and radar, all of which need to be processed instantly to make safe driving decisions. If this data had to travel to a distant server and back, the delay could be catastrophic. Edge computing allows the vehicle to process this information on board, making split-second decisions without network lag. Similarly, in smart factories, edge computing enables real-time monitoring and control of machinery. Imagine a robotic arm on an assembly line. Edge computing allows it to adjust its movements based on immediate feedback from sensors, optimizing performance and preventing defects. This not only speeds up production but also enhances safety by quickly responding to anomalies. In remote healthcare, where continuous monitoring of patients via wearable devices is becoming increasingly common, edge computing plays a vital role. These devices can analyze a patient's vital signs in real time, alerting healthcare providers to potential emergencies without delay. This immediate response can be life-saving, especially in rural areas where access to medical facilities is limited. Beyond reducing latency, edge computing also enhances security. By processing data locally, sensitive information doesn't need to be transmitted over a network, reducing the risk of interception. This is especially important in industries like finance and healthcare, where data privacy is paramount. Additionally, processing data closer to the source minimizes network congestion, improving responsiveness and reliability. This is beneficial in environments with limited bandwidth or unreliable internet connectivity. As cyber-physical systems continue to evolve, edge computing will undoubtedly play an increasingly vital role, enabling faster, more secure, and more efficient operations across a wide range of industries. This sets the stage for our next concept, where we'll transform the conversation into digital twins and how they mirror physical assets in the digital world. Turning our attention now to the realm of virtual replication, the second concept explores digital twins for physical assets. A digital twin is exactly what it sounds like, a virtual replica of a physical asset, system, or process. This isn't just a simple 3D model. It's a dynamic, living model that updates in real time with data from its physical counterpart, offering a comprehensive view of its performance, condition, and behavior. One of the most significant applications of digital twins is in predictive maintenance. By continuously monitoring data from sensors on a physical asset, the digital twin can identify patterns and anomalies that indicate potential failures. This allows maintenance teams to address issues before they lead to downtime, saving time and resources. For instance, General Electric uses digital twins of aircraft engines to predict when specific components might need replacement, optimizing maintenance schedules and extending engine lifespan. Performance optimization is another key benefit. Digital twins enable engineers to simulate different operating conditions and scenarios to identify the most efficient settings for a physical asset. This is particularly valuable in industries such as energy, where even small improvements in efficiency can result in significant cost savings. Wind farms, for example, can use digital twins to optimize the angle of turbine blades based on real-time wind conditions, maximizing energy production. Moreover, digital twins are incredibly useful for simulating real-world scenarios. Before implementing changes to a physical system, engineers can test them virtually using the digital twin, minimizing the risk of unexpected outcomes. This is crucial in complex environments such as urban infrastructure projects. Cities are increasingly using digital twins to simulate the impact of new buildings, transportation systems, and other infrastructure projects on traffic flow, energy consumption, and environmental conditions. This allows city planners to make informed decisions and avoid costly mistakes. From aerospace to manufacturing to urban planning, digital twins are transforming industries by providing insights that were previously impossible to obtain. This real-time, data-driven approach enhances decision-making, improves efficiency, and reduces risk. And now, as we transition from virtual replicas to intelligent forecasting, we explore how artificial intelligence drives predictive maintenance, optimizing operations and minimizing downtime. The third practice involves artificial intelligence-driven predictive maintenance. Delving into the world of predictive maintenance, artificial intelligence and machine learning algorithms become invaluable tools, analyzing sensor data from cyber-physical systems to forecast equipment failures and fine-tune maintenance schedules. This proactive approach marks a significant shift from reactive maintenance, where repairs are only made after a breakdown occurs, and preventative maintenance, which follows a predetermined schedule regardless of the actual condition of the equipment. One of the primary applications of artificial intelligence-driven predictive maintenance is within the manufacturing sector. Factories are filled with complex machinery, and unexpected downtime can halt production and result in substantial financial losses. By using artificial intelligence algorithms to analyze data from sensors monitoring vibration, temperature, and other critical parameters, manufacturers can predict when a machine component is likely to fail. This allows them to schedule maintenance during planned downtime, minimizing disruptions and maximizing productivity. The transportation industry also benefits greatly from artificial intelligence-driven predictive maintenance. Airlines, for example, use artificial intelligence to analyze data from sensors on aircraft engines, predicting when specific parts will need to be replaced or repaired. This not only reduces the risk of in-flight engine failures, but also optimizes maintenance schedules, ensuring that aircraft are available when needed. Similarly, in the energy sector, artificial intelligence is used to monitor the health of critical infrastructure such as power plants and transmission lines. By analyzing data from sensors and other sources, energy companies can predict when equipment is likely to fail and take proactive measures to prevent outages. This is particularly important for maintaining a reliable supply of electricity to homes and businesses. several types of artificial intelligence models are commonly used in predictive maintenance. Regression models, for instance, can be trained to predict the remaining useful life of a component based on its current condition and historical data. Neural networks, on the other hand, are capable of learning complex patterns and relationships in data, making them well-suited for identifying subtle indicators of potential failures. These models can analyze vast amounts of data from multiple sources, providing insights that would be impossible for humans to detect. The benefits of artificial intelligence-driven predictive maintenance are clear: reduced downtime, increased operational efficiency, and cost savings. By predicting equipment failures before they occur, organizations can minimize disruptions, optimize maintenance schedules, and extend the lifespan of their assets. This translates to significant improvements in productivity, profitability, and overall performance. Armed with insights into optimizing maintenance with artificial intelligence, we will now transition to exploring secure data integration platforms and how they ensure seamless data exchange between diverse cyber-physical system components and enterprise systems, enhancing overall system integrity and security. The fourth concept underscores the critical role of secure data integration platforms. These platforms are essential for enabling smooth and secure data exchange between the various components of cyber-physical systems and broader enterprise systems. Imagine a smart factory where robots, sensors, and management software all need to communicate seamlessly. A secure data integration platform acts as the central nervous system, ensuring that data flows efficiently and securely between these diverse elements. However, integrating data from different sources and systems presents significant security challenges. Cyber-physical systems often involve a mix of legacy devices, modern sensors, and cloud-based applications, each with its own security vulnerabilities. A secure data integration platform must address these challenges head-on, providing robust mechanisms to protect data from unauthorized access, tampering, and theft. Encryption is a cornerstone of secure data integration. By encrypting data both in transit and at rest, organizations can prevent unauthorized parties from reading sensitive information. Access control is another critical component, ensuring that only authorized users and systems can access specific data resources. This involves implementing strong authentication mechanisms such as multi-factor authentication and role-based access control. Identity management plays a vital role in verifying the identity of users and devices attempting to access data. By using digital certificates and other identity management technologies, organizations can ensure that only trusted entities are allowed to participate in data exchange. Beyond these technical measures, secure data integration also requires strong policies and procedures. Organizations must establish clear guidelines for data governance, access control, and incident response. Regular security audits and penetration testing are essential for identifying and addressing potential vulnerabilities. The role of secure data integration platforms extends beyond simply protecting data. It also ensures data integrity, confidentiality, and availability during the integration process. Data integrity means that data remains accurate and complete as it moves between systems. Confidentiality ensures that sensitive data is only accessible to authorized parties, and availability means that data is readily accessible when needed. These three pillars are essential for building trust and confidence in cyber-physical systems. Now that we have explored the importance of secure data integration platforms, let's delve into how blockchain technology can further enhance the security and transparency of cyber-physical systems data and transactions. Expanding on our exploration of security measures, let's examine how blockchain technology bolsters the security and transparency of cyber-physical systems data and transactions. Blockchain, originally conceived as the backbone for cryptocurrencies, offers unique features that make it incredibly valuable for securing cyber-physical systems. At its core, a blockchain is a distributed, immutable ledger that records transactions in a secure and transparent manner. Each transaction is grouped into a block, which is then cryptographically linked to the previous block, creating a chain of blocks that is virtually tamper-proof. This immutability is one of blockchain's key strengths. Once data is recorded on the blockchain, it cannot be altered or deleted, providing a permanent and auditable record of all transactions. This is particularly useful in cyber-physical systems where data integrity is paramount. Consider a supply chain management application. By recording each step of the supply chain on a blockchain, from manufacturing to delivery, organizations can ensure the authenticity and provenance of goods. This can help prevent counterfeiting, reduce fraud, and improve overall supply chain efficiency. Smart contracts are another key application of blockchain in cyber-physical systems. These are self-executing contracts written in code and stored on the blockchain. They automatically enforce the terms of an agreement when predefined conditions are met. In a cyber-physical system context, smart contracts can be used to automate various processes and ensure compliance with regulations. For example, in a smart grid, smart contracts can be used to automate energy trading between producers and consumers, ensuring fair pricing and efficient energy distribution. Secure data sharing among cyber-physical system devices is also enhanced by blockchain. Traditional data sharing methods often involve centralized servers which can be vulnerable to attacks. Blockchain, on the other hand, enables decentralized data sharing where data is distributed across multiple nodes in the network. This reduces the risk of a single point of failure and makes it more difficult for attackers to compromise the system. The benefits of blockchain in cyber-physical systems extend beyond security. The distributed consensus mechanism used by blockchain ensures that all participants in the network agree on the validity of transactions. This eliminates the need for a central authority and promotes trust among participants. The cryptographic protection provided by blockchain ensures that data is encrypted and protected from unauthorized access. This is particularly important in cyber-physical systems where sensitive data is often collected and transmitted. As we continue to look at the future, managing a large number of Internet of Things devices in cyber-physical system environments presents its own unique set of challenges. Transitioning from blockchain security benefits, let's consider the multifaceted challenges of Internet of Things device management at scale within cyber-physical systems environments. In cyber-physical systems, the sheer volume of Internet of Things devices presents significant management complexities. These devices, which are integral to collecting and transmitting data, require careful oversight to function correctly and securely. Device provisioning, the process of securely onboarding new devices into the network, is the first hurdle. Each device needs to be authenticated and configured with the correct settings to ensure it can communicate effectively with other components of the system. This process must be streamlined to handle thousands or even millions of devices efficiently. Configuration is an ongoing task. Devices need to be configured and reconfigured as their roles change or as the system evolves. This includes setting communication parameters, security policies, and data collection intervals. Managing these configurations across a large number of devices can be a logistical nightmare without the right tools. Monitoring is crucial for maintaining the health and performance of Internet of Things devices. Real-time monitoring enables operators to detect anomalies, identify failing devices, and proactively address potential issues before they impact the system. This requires robust monitoring infrastructure and analytics capabilities. Remote software updates are essential for patching security vulnerabilities and adding new features to Internet of Things devices. However, deploying updates to a large fleet of devices can be challenging, especially if the devices are geographically dispersed or have limited connectivity. Device management platforms play a pivotal role in addressing these challenges. These platforms provide a centralized interface for managing all aspects of the device lifecycle, from provisioning to retirement. They offer features such as remote configuration, over-the-air software updates, and real-time monitoring. Protocols like message queuing telemetry transport, or MQTT, and constrained application protocol, or CoAP, are commonly used in conjunction with these platforms. MQTT is a lightweight publish-subscribe messaging protocol that is well suited for Internet of Things devices with limited bandwidth and processing power. CoAP is another lightweight protocol designed for constrained environments, offering features such as resource discovery and support for web standards. Together, device management platforms and protocols enable efficient device lifecycle management. They automate many of the manual tasks associated with device management, reducing the burden on operators and improving overall system efficiency. They also ensure that devices remain secure and up-to-date, minimizing the risk of cyber attacks. As we continue to explore the cyber-physical system landscape, the ability to extract real-time insights from the vast streams of data generated by these devices becomes increasingly critical. Now, pivoting to another crucial aspect of cyber-physical systems, real-time data analytics becomes indispensable for extracting actionable insights from the continuous streams of data that cyber-physical systems generate. This capability allows for immediate decision-making and optimization, which are fundamental to the efficiency and responsiveness of these systems. Several analytical techniques are employed to achieve this. Streaming analytics involves the continuous processing of data as it arrives, enabling immediate insights and actions. This is particularly useful in scenarios where delayed analysis would render the data irrelevant. Complex event processing, or CEP, is another technique that identifies meaningful patterns and relationships within high-volume data streams. CP engines can detect sequences of events, temporal relationships, and other complex patterns that indicate important situations or trends. Anomaly detection is used to identify deviations from expected behavior. This is critical for identifying potential faults, security breaches, or other abnormal conditions that require immediate attention. These techniques find applications across various sectors. In smart grids, real-time data analytics is used to monitor grid stability, optimize energy distribution, and detect anomalies that could indicate equipment failures or cyber attacks. By analyzing data from sensors and smart meters in real time, grid operators can make informed decisions to maintain grid reliability and prevent blackouts. Traffic management systems leverage real-time data analytics to optimize traffic flow, reduce congestion, and improve safety. By analyzing data from traffic sensors, cameras, and connected vehicles, these systems can dynamically adjust traffic signals, provide real-time traffic information to drivers, and detect incidents that require immediate response. Industrial automation benefits significantly from real-time data analytics, enabling predictive maintenance, process optimization, and quality control. By analyzing data from sensors and equipment in manufacturing facilities, operators can identify potential equipment failures before they occur, optimize production processes to improve efficiency, and detect defects in real time, reducing waste and improving product quality. The ability to process and analyze data in real time enables timely decision-making. For example, in a smart grid, detecting a sudden surge in demand allows operators to activate additional resources to prevent a grid overload. In a traffic management system, identifying a major accident allows the system to reroute traffic and alert emergency services, minimizing the impact of the incident. Real-time data analytics also plays a crucial role in optimizing system performance. By continuously monitoring key performance indicators, or KPI, and identifying areas for improvement, organizations can fine-tune their operations to achieve greater efficiency and productivity. Whether it's adjusting energy distribution in a smart grid or optimizing production processes in a factory, real-time insights enable continuous improvement and adaptation. Moving forward, the enhancements in connectivity provided by 5G and wireless communication technologies will further revolutionize cyber-physical systems. With a stage set for advanced connectivity, the role of 5G and other wireless communication technologies in cyber-physical systems is transformative. These technologies enable the low latency and high bandwidth connectivity essential for cyber-physical systems to operate effectively. 5G is particularly well suited to support applications that require real-time interactions and massive data throughput. Autonomous vehicles represent a prime example of where 5G connectivity is crucial. These vehicles require constant communication with their environment, including other vehicles, traffic management systems, and cloud-based services. The low latency of 5G ensures that commands and data are transmitted and received with minimal delay, enabling quick decision-making and enhancing safety. High bandwidth allows for the transmission of large amounts of sensor data, maps, and video feeds necessary for navigation and control. Remote robotics also benefits significantly from 5G connectivity. In applications such as remote surgery, bomb disposal, and hazardous environment exploration, precise control and real-time feedback are essential. 5G provides the necessary bandwidth and low latency to enable operators to remotely control robots with a high degree of accuracy and responsiveness, as if they were physically present. Augmented reality-based maintenance is another area where 5G can enhance cyber-physical systems. By overlaying digital information onto the physical world, augmented reality provides technicians with real-time guidance and support for maintenance and repair tasks. 5G's high bandwidth ensures that large augmented reality datasets can be transmitted quickly and reliably, enabling technicians to diagnose and resolve issues more efficiently. 5G's architecture is designed to support massive machine-type communication, or MMTC, which enables the connection of a very large number of devices. This is particularly important for cyber-physical systems that involve numerous sensors, actuators, and other devices. With MMTC, cyber-physical systems can scale to accommodate a growing number of connected devices without sacrificing performance or reliability. Ultra-reliable low-latency communication, or ULC, is another key feature of 5G that is critical for cyber-physical systems. ULC provides extremely low latency and high reliability, ensuring that critical communications are delivered with virtually no delay and minimal risk of interruption. This is essential for applications such as industrial automation, where even a brief delay or interruption could have significant consequences. The capabilities of 5G and other advanced wireless communication technologies are unlocking new possibilities for cyber-physical systems. From enabling autonomous vehicles to supporting remote robotics and augmented reality-based maintenance, these technologies are paving the way for more connected, efficient, and intelligent systems. As we look ahead, human-machine interface design will play a crucial part in how we interact with these increasingly sophisticated systems. Transitioning our focus from the network infrastructure to the user's experience, the design of human-machine interfaces becomes paramount. Intuitive and user-friendly human-machine interfaces are essential for enabling effective interaction between humans and cyber-physical systems. A well-designed human-machine interface can enhance usability, improve safety, and increase overall system efficiency. Usability is a core principle of human-machine interface design and refers to the ease with which users can accomplish their tasks. Key aspects of usability include learnability, efficiency, memorability, error prevention, and satisfaction. Learnability ensures that new users can quickly become proficient with the interface. Efficiency enables experienced users to perform tasks quickly and with minimal effort. Memorability ensures that users can easily remember how to use the interface after a period of not using it. Error prevention helps to minimize mistakes and provides clear and helpful error messages when they do occur. Satisfaction refers to the overall pleasantness and user experience while using the interface. Accessibility is another critical design principle which ensures that the human-machine interfaces are usable by people with a wide range of abilities and disabilities. This includes providing alternative input methods, adjustable font sizes, screen reader compatibility, and clear visual cues. Accessible human-machine interfaces not only improve the user experience for people with disabilities, but also enhance usability for all users. Cognitive ergonomics focuses on designing the human-machine interface to align with human cognitive abilities and limitations. This involves understanding how users perceive, process, and remember information, and designing the interface accordingly. Key considerations in cognitive ergonomics include minimizing cognitive load, providing clear and consistent feedback, and avoiding information overload. In industrial control systems, human-machine interfaces are used to monitor and control complex processes such as manufacturing, energy production, and water treatment. These interfaces provide operators with real-time data visualization, alarm management, and control functions. Effective human-machine interface design in industrial control systems is crucial for ensuring safety, preventing equipment failures, and optimizing system performance. Healthcare devices such as patient monitors, infusion pumps, and diagnostic equipment rely on intuitive human-machine interfaces to enable healthcare professionals to deliver high-quality care. These interfaces must be designed to minimize errors, provide clear and concise information, and support efficient workflows. Human-machine interface design in healthcare is particularly critical, as errors can have serious consequences for patient safety. In smart home environments, human-machine interfaces are used to control lighting, temperature, security systems, and appliances. These interfaces often take the form of touchscreen panels, voice assistants, or mobile apps. User-friendly human-machine interfaces in smart homes enhance convenience, improve energy efficiency, and provide peace of mind. The design of human-machine interfaces plays a crucial role in enhancing user experience and safety across a wide range of cyber-physical system applications. By focusing on usability, accessibility, and cognitive ergonomics, designers can create interfaces that are intuitive, efficient, and enjoyable to use. As we continue to integrate cyber-physical systems into more aspects of our lives, the importance of well-designed human-machine interfaces will only continue to grow, leading us to the integration of autonomous robots and automation. Transitioning from the user's interaction with cyber-physical systems, our attention now shifts to the operational backbone that drives much of the progress in this field. Autonomous robotics and automation are revolutionizing industries such as manufacturing, logistics, and agriculture by introducing new levels of efficiency, precision, and adaptability. In manufacturing, autonomous robots are used for tasks such as assembly, welding, and painting, performing repetitive and often dangerous jobs with consistent quality and speed. Integrated with cyber-physical systems, these robots can communicate with each other and with central control systems, optimizing workflows and adapting to changing production needs in real time. The integration of robots with cyber-physical systems enables manufacturers to achieve greater flexibility and responsiveness, leading to increased efficiency and reduced costs. In logistics, automated systems are transforming warehousing and distribution operations through automated guided vehicles, robotic pickers, and drone delivery systems. These technologies enable faster order fulfillment, reduced errors, and improved inventory management. Cyber-physical systems play a crucial role in coordinating these automated logistics operations, integrating data from sensors, cameras, and tracking systems to optimize routes, manage inventory levels, and ensure timely delivery. The result is a more efficient and resilient supply chain that can adapt to changing demand patterns and disruptions. In agriculture, autonomous robots are used for tasks such as planting, harvesting, and crop monitoring, addressing labor shortages and improving yield. These robots can operate autonomously in the field, using sensors and computer vision to identify and target specific plants, apply fertilizers and pesticides with precision, and collect data on crop health and environmental conditions. The integration of robots with cyber-physical systems enables farmers to optimize their operations based on real-time data, reducing waste, conserving resources, and improving overall productivity. Key technologies driving autonomous robotics and automation include computer vision, which allows robots to perceive and interpret their environment, sensor fusion, which combines data from multiple sensors to create a more complete and accurate understanding of the robot's surroundings, and path planning algorithms, which enable robots to navigate complex environments and avoid obstacles. These technologies are constantly evolving, leading to more sophisticated and capable robots that can perform a wider range of tasks with greater autonomy and precision. The benefits of autonomous robotics and automation extend beyond increased productivity and reduced labor costs. These technologies also improve safety by removing humans from hazardous environments, reducing the risk of accidents and injuries. Now, with robots taking on more tasks, it's time to consider how we protect these systems and the data they handle, which leads us to exploring cyber-physical security frameworks. The 11th concept zeroes in on the crucial need for robust cyber-physical security frameworks to shield cyber-physical systems from cyber threats and ensure overall system resilience. Critical infrastructures, smart manufacturing plants, and advanced healthcare systems all rely on the seamless integration of cyber and physical components. However, this integration also creates vulnerabilities that malicious actors can exploit, potentially leading to devastating consequences. Therefore, implementing comprehensive security frameworks is paramount to protecting cyber-physical systems from a wide range of cyber threats, including malware, ransomware, and denial-of-service attacks. Several security frameworks offer guidance and best practices for securing cyber-physical systems. The National Institute of Standards and Technology Cybersecurity Framework, often called NIST Cybersecurity Framework, provides a risk-based approach to cybersecurity management, enabling organizations to assess their cybersecurity posture, identify gaps, and implement appropriate security controls. It comprises 5 core functions: identify, protect, detect, respond, and recover, covering the entire cybersecurity lifecycle. Another widely recognized framework is International Electrotechnical Commission 62443, known as IC 62443, which focuses specifically on the security of industrial automation and control systems. It provides detailed guidance on security requirements, security levels, and security assurance for various components of industrial control systems. Organizations can use these frameworks to establish a baseline for security and continuously improve their security posture over time. Risk assessment, security policies, and incident response planning are essential components of any cyber-physical security framework. Risk assessment involves identifying potential threats and vulnerabilities, assessing the likelihood and impact of successful attacks, and prioritizing security measures based on risk levels. Security policies define the rules and procedures that govern the behavior of users, systems, and networks, providing a framework for consistent security practices across the organization. Incident response planning involves developing procedures for detecting, analyzing, containing, and recovering from security incidents, enabling organizations to respond quickly and effectively to minimize damage and restore normal operations. These measures are crucial steps in mitigating cyber-physical risks. Now, with robust cyber-physical security frameworks in place, we must discuss the handling of data within cyber-physical systems and turn the page to data governance and compliance. As we pivot from security to stewardship, let's delve into the 12th concept, data governance and compliance. In managing cyber-physical systems data responsibly and ethically, data governance and compliance are not merely procedural formalities but critical pillars. The increasing volume and complexity of data generated by cyber-physical systems demand stringent governance frameworks to ensure its integrity, security, and ethical use. Organizations must establish clear policies and procedures for data collection, storage, processing, and sharing to comply with evolving regulatory requirements and maintain public trust. Regulations such as the General Data Protection Regulation, also known as GDPR, in Europe and the California Consumer Privacy Act, also known as CCPA in the United States, have significant implications for cyber-physical systems data. The General Data Protection Regulation, for example, mandates that organizations obtain explicit consent before collecting and processing personal data, provide transparency about data processing activities, and grant individuals the right to access, rectify, and erase their data. The California Consumer Privacy Act grants similar rights to California residents, including the right to know what personal information is collected about them, the right to opt out of the sale of their personal information, and the right to equal service and price even if they exercise their privacy rights. Transparency, consent, and data minimization are crucial principles in ensuring compliance with data protection laws. Transparency requires organizations to be open and honest about how they collect, use, and share data. Consent involves obtaining individuals' explicit agreement before collecting and processing their personal data. Data minimization entails collecting only the data that is necessary for the specified purpose, minimizing the risk of privacy breaches and misuse. Compliance with these principles requires organizations to implement robust data governance practices, including data inventory, data classification, data access controls, and data retention policies. With these principles firmly established, let's shift our focus to how these systems can be designed for maximum efficiency. We'll discuss energy-efficient cyber-physical systems design, ensuring a lighter environmental footprint. Turning our attention from data governance to environmental responsibility, energy-efficient cyber-physical systems design emerges as our 13th concept. Given the escalating concerns about climate change and resource depletion, energy efficiency is paramount. Cyber-physical systems, while offering unprecedented capabilities, can also be significant energy consumers. Therefore, integrating energy-efficient design principles into their development is imperative for creating sustainable and environmentally friendly technologies. Reducing energy consumption in cyber-physical system devices, networks, and systems involves employing a multifaceted approach that addresses various aspects of their architecture and operation. One technique involves optimizing the hardware components used in cyber-physical system devices. This includes selecting low-power microcontrollers, sensors, and communication modules that minimize energy consumption during operation. Power management techniques such as dynamic voltage and frequency scaling, also known as DVFS, can be employed to adjust the voltage and frequency of processors based on workload demands, reducing energy consumption during periods of low activity. Similarly, sleep modes and wake-up mechanisms can be implemented to minimize idle power consumption by putting devices into a low power state when not actively performing tasks. Another strategy focuses on optimizing the communication protocols and network infrastructure used in cyber-physical systems. Wireless communication technologies such as Bluetooth Low Energy, also known as BLE, and Zigbee, are designed for low power operation and are suitable for many cyber-physical system applications. Energy-efficient routing algorithms and data aggregation techniques can also minimize the amount of data transmitted over the network, reducing communication overhead and energy consumption. For example, in smart buildings, occupancy sensors can be used to detect when rooms are unoccupied and automatically turn off lights and adjust heating, ventilation, and air conditioning, also known as HVAC systems, reducing energy waste. Considering specific applications, smart buildings exemplify energy-efficient cyber-physical systems in action. These buildings integrate sensors, controllers, and data analytics to optimize energy consumption based on real-time conditions and occupancy patterns. Renewable energy systems, such as solar photovoltaic arrays and wind turbines, can be integrated into cyber-physical systems to provide clean, sustainable power. Electric vehicles represent another area where cyber-physical systems play a crucial role in optimizing energy usage and extending driving range. Advanced control algorithms, battery management systems, and regenerative braking technologies are employed to maximize energy efficiency and minimize energy waste. Their integration demonstrates significant advancements in energy management, but what about aiding disaster recovery? Transitioning from discussions of energy conservation, let's now turn our attention to another transformative domain: cyber-physical systems in smart healthcare. The integration of cyber-physical systems is revolutionizing healthcare delivery and significantly improving patient outcomes. Remote patient monitoring stands as a prime example, allowing healthcare providers to track patients' vital signs and health status remotely through wearable sensors and connected devices. This is particularly beneficial for managing chronic conditions such as diabetes, hypertension, and heart failure, as it enables timely interventions and reduces the need for frequent hospital visits. Robotic surgery is another groundbreaking application, enhancing surgical precision, minimizing invasiveness, and shortening recovery times. Surgical robots, equipped with advanced imaging and control systems, enable surgeons to perform complex procedures with greater accuracy and dexterity. These systems reduce the risk of complications and improve surgical outcomes, allowing patients to return to their normal lives more quickly. Smart drug delivery systems represent another innovative application of cyber-physical systems in healthcare. These systems utilize microsensors, micropumps, and feedback control mechanisms to deliver drugs directly to the targeted tissues or organs, optimizing therapeutic efficacy and minimizing side effects. For example, implantable drug delivery systems can provide continuous, controlled release of medications for chronic pain management or cancer treatment, improving patient compliance and quality of life. The benefits of cyber-physical systems in smart healthcare extend beyond technological advancements, encompassing increased access to care, improved accuracy and efficiency, and personalized treatment plans. Remote patient monitoring expands healthcare access to rural and underserved populations, while robotic surgery enhances surgical precision and efficiency. Smart drug delivery systems enable personalized treatment approaches tailored to individual patient needs, optimizing therapeutic outcomes. However, the widespread adoption of cyber-physical systems in healthcare also presents significant challenges related to data privacy, security, and regulatory compliance. The collection, storage, and transmission of sensitive patient data raise concerns about privacy breaches and unauthorized access. Robust security measures such as encryption, access control, and intrusion detection systems are essential to protect patient data and maintain confidentiality. Regulatory compliance with standards such as the Health Insurance Portability and Accountability Act, also known as HIPAA, and General Data Protection Regulation, also known as GDPR, is crucial to ensure that cyber-physical systems in healthcare adhere to data protection laws and ethical guidelines. With that area of medicine explored, the next concept involves another vital framework. Stepping from the world of smart healthcare, we now explore how cyber-physical systems are reshaping urban landscapes into smart cities. Cyber-physical systems are instrumental in creating urban environments that are more efficient, sustainable, and livable. Consider smart transportation as a cornerstone of the smart city concept, leveraging cyber-physical systems to optimize traffic flow, reduce congestion, and enhance mobility. Intelligent transportation systems use sensors, cameras, and communication networks to collect real-time data on traffic conditions, pedestrian movements, and public transportation schedules. This data is then analyzed to dynamically adjust traffic signals, optimize routes, and provide travelers with up-to-date information via mobile apps and digital displays. Smart energy grids represent another critical application, integrating renewable energy sources, optimizing energy distribution, and reducing energy consumption. Smart grids utilize sensors, smart meters, and control systems to monitor energy demand and supply in real time. This enables utilities to balance the grid, detect and respond to outages, and integrate distributed generation sources such as solar and wind power. Consumers benefit from smart grids through time-of-use pricing, energy management tools, and the ability to participate in demand response programs. Smart waste management systems utilize sensors, robotics, and data analytics to optimize waste collection, reduce landfill waste, and promote recycling. Smart waste bins equipped with sensors monitor fill levels and communicate with waste collection trucks to optimize collection routes. Automated sorting systems use robotics and artificial intelligence to separate recyclable materials from waste streams, increasing recycling rates and reducing the amount of waste sent to landfills. Data analytics provide insights into waste generation patterns, enabling cities to implement targeted waste reduction programs. The benefits of cyber-physical systems in smart cities are far-reaching, encompassing improved resource utilization, reduced congestion, and enhanced quality of life. Smart transportation systems reduce traffic congestion, decrease travel times, and improve air quality. Smart energy grids optimize energy consumption, reduce carbon emissions, and enhance grid reliability. Smart waste management systems minimize waste, promote recycling, and reduce environmental pollution. Data analytics, Internet of Things devices, and communication networks play a crucial role in enabling smart city cyber-physical systems, providing the data, connectivity, and intelligence needed to optimize urban operations and services. With our cities becoming more connected, the next concept considers how to ensure these systems from different sources work together seamlessly. Advancing from the concept of connected smart cities, we now turn our attention to standardization and interoperability, which are essential for enabling the smooth integration of cyber-physical systems components from various vendors. Standardization ensures that cyber-physical systems components adhere to common specifications and protocols, facilitating seamless communication and data exchange among devices and systems, while interoperability ensures that these components can work together effectively, regardless of their manufacturer or underlying technology. Standardization efforts by organizations such as the Institute of Electrical and Electronics Engineers, the International Organization for Standardization, and the International Electrotechnical Commission play a crucial role in defining standards for cyber-physical systems development and deployment. These standards cover various aspects, including communication protocols, data formats, security requirements, and performance metrics. The Institute of Electrical and Electronics Engineers, for example, develops standards for wireless communication, power systems, and automation, which are widely used in cyber-physical systems applications. The International Organization for Standardization develops standards for quality management, environmental management, and information security, ensuring that cyber-physical systems meet international best practices. The International Electrotechnical Commission develops standards for electrical and electronic equipment, including sensors, actuators, and control systems used in cyber-physical systems. Open standards promote innovation by providing a level playing field for vendors and developers, allowing them to create interoperable components without being locked into proprietary technologies. This fosters competition, drives down costs, and accelerates the development of new cyber-physical systems applications. Open standards also ensure compatibility among cyber-physical systems devices and systems, regardless of their manufacturer or underlying technology. This enables organizations to mix and match components from different vendors, creating customized cyber-physical systems solutions that meet their specific needs. As we ensure the framework for cyber-physical systems, it's also crucial to understand the moral compass that guides their use. Turning our attention to the ethical landscape, ethical considerations in cyber-physical systems highlight the critical need to address the implications of these technologies, focusing on key areas such as privacy, security, autonomy, and accountability. As cyber-physical systems become more integrated into our lives, they collect and process vast amounts of personal data, raising concerns about privacy violations and potential misuse of information. For example, smart home devices equipped with sensors and cameras can monitor residents' activities, raising questions about data security and unauthorized access. Similarly, wearable health monitors can track individuals' health metrics, potentially leading to discrimination by insurance companies or employers. Security is another paramount ethical concern in cyber-physical systems, as vulnerabilities in these systems can have far-reaching consequences. Cyber attacks targeting critical infrastructure, such as power grids or transportation networks, can disrupt essential services and endanger public safety. Autonomous systems, such as self-driving cars and robots, raise complex ethical dilemmas related to decision-making in unforeseen conditions. For instance, in an unavoidable accident scenario, how should an autonomous vehicle prioritize the safety of its occupants versus pedestrians? Accountability is crucial in ensuring that individuals and organizations are held responsible for the actions and outcomes of cyber-physical systems. When autonomous systems make decisions that cause harm, determining who is responsible can be challenging. Is it the manufacturer, the programmer, or the operator? Clear lines of accountability are needed to address these issues and ensure that victims have recourse. To address these ethical concerns, it is imperative to develop ethical guidelines and regulations that ensure cyber-physical systems are used responsibly and do not infringe on human rights or values. These guidelines should emphasize transparency, fairness, and public engagement in shaping the future of cyber-physical systems. Transparency ensures that individuals understand how cyber-physical systems collect, use, and share their data. Fairness ensures that cyber-physical systems do not discriminate against individuals or groups based on factors such as race, gender, or socioeconomic status. Public engagement involves actively soliciting input from diverse stakeholders, including experts, policymakers, and the general public, to ensure that ethical considerations are integrated into the design and deployment of cyber-physical systems. As we look at the societal impact of these sophisticated systems, it is also important to understand how they can aid in times of crisis. Transitioning to a critical application of cyber-physical systems, cyber-physical systems for disaster response significantly enhance our ability to manage and recover from various crises. Drone-based search and rescue operations mark a significant advancement, offering rapid and extensive aerial surveillance to locate victims in disaster-stricken areas. Equipped with high-resolution cameras and thermal sensors, drones can navigate through collapsed structures and hazardous environments, identifying survivors who may be unreachable by traditional methods. These drones relay real-time imagery and data to rescue teams, enabling them to strategically plan and execute rescue missions, thereby increasing the chances of saving lives. Sensor networks for monitoring environmental conditions represent another vital component of cyber-physical systems in disaster response. These networks consist of interconnected sensors strategically deployed to gather data on critical environmental parameters, such as air quality, water levels, and structural integrity of buildings. During a natural disaster like a flood or earthquake, these sensors provide real-time information on rising water levels, potential landslides, and structural damage across affected regions. This data enables emergency responders to assess the scope and severity of the disaster, optimize resource allocation, and implement timely evacuation plans, helping to minimize the impact on communities. Communication systems are essential for coordinating emergency services during disaster response efforts. These systems facilitate seamless communication and data sharing among various stakeholders, including first responders, government agencies, and volunteer organizations. Advanced communication platforms enable real-time information exchange, allowing teams to coordinate search and rescue operations, allocate resources effectively, and provide timely assistance to those in need. The ability to maintain reliable communication networks during disasters is crucial for ensuring that emergency services can operate efficiently and save lives. The benefits of real-time situational awareness, improved coordination, and faster response times are central to the use of cyber-physical systems in disaster management. By providing immediate access to critical information, cyber-physical systems enable decision-makers to make informed choices and allocate resources effectively. This leads to improved coordination among different agencies and organizations, ensuring that efforts are synchronized and resources are utilized efficiently. The result is faster response times, enabling rescue teams to reach victims more quickly and provide timely assistance, ultimately saving lives and minimizing damage. As we equip ourselves with the tools to understand and respond to disaster, we must also prepare a skilled workforce to manage these technologies in the future. Now, turning our attention to the future, we consider the education and workforce development necessary to support cyber-physical systems, alongside a look at the emerging trends that will shape this field. For cyber-physical systems education and workforce development, the demand for skilled professionals who can design, develop, and deploy these sophisticated systems is rapidly growing. Educational programs are crucial in equipping the next generation with the skills needed to navigate the complexities of cyber-physical systems. Universities and vocational schools are increasingly offering specialized courses and degrees focused on areas such as robotics, data analytics, and cybersecurity, all tailored to meet the unique challenges presented by cyber-physical systems. Training initiatives also play a vital role, providing hands-on experience and practical knowledge that complements academic learning. Industry partnerships are becoming more common, allowing students and professionals to work on real-world projects and gain invaluable insights into the application of cyber-physical systems. Workforce development strategies are essential for cultivating a workforce that is not only technically proficient, but also capable of adapting to the evolving landscape of cyber-physical systems. These strategies include continuous learning programs, certification courses, and mentorship opportunities, which help professionals stay abreast of the latest advancements and best practices. As for future trends in cyber-physical systems, several exciting possibilities are on the horizon, promising to revolutionize industries and enhance our daily lives. The integration of quantum computing holds immense potential, offering unparalleled processing power to tackle complex problems in optimization, simulation, and cryptography. Quantum-enhanced cyber-physical systems could lead to breakthroughs in areas such as autonomous vehicles, drug discovery, and financial modeling, enabling us to solve previously intractable challenges. Nanotechnology is another emerging trend that could significantly impact cyber-physical systems. By creating nanoscale devices and materials, we can develop more efficient sensors, actuators, and energy storage systems. Nanoscale sensors embedded in infrastructure, for example, could provide real-time monitoring of structural health, enabling proactive maintenance and preventing catastrophic failures. Bio-inspired designs are also gaining traction, drawing inspiration from nature to create more resilient, adaptable, and energy-efficient cyber-physical systems. By mimicking biological systems, we can develop robots that navigate complex environments, algorithms that optimize resource allocation, and materials that self-heal. These bio-inspired approaches could lead to innovative solutions in areas such as healthcare, manufacturing, and environmental conservation, addressing some of the current challenges and pushing the boundaries of what is possible. Having explored the future potential and necessities of these systems, let's wrap up our discussion with a final summary. In summary, the journey through these 20 key concepts has illuminated the transformative power of cyber-physical systems and data integration. We've explored edge computing enabling real-time decisions, digital twins mirroring physical assets, and artificial intelligence driving predictive maintenance. The critical role of secure data integration platforms and blockchain in ensuring cyber-physical system security has been highlighted, alongside effective Internet of Things device management at scale. We investigated the impact of real-time data analytics, the connectivity revolution brought by 5G, and the necessity of intuitive human-machine interface design. Discussing the advances in autonomous robotics and automation, we also emphasized the importance of robust cyber-physical security frameworks and diligent data governance and compliance. We considered the design of energy-efficient cyber-physical systems, along with their applications in smart healthcare and the construction of smart cities. Focusing on the need for standardization and interoperability, we addressed the ethical considerations inherent in cyber-physical systems and their vital role in disaster response. Finally, we examined cyber-physical systems education and workforce development, and we anticipated future trends that promise to reshape cyber-physical systems significantly. These concepts collectively hold the potential to revolutionize how we interact with technology, reshaping industries, enhancing productivity, and ultimately improving quality of life. Now it's your turn. How do you see these technologies impacting your daily routines or professional field? What innovative applications can you envision? We invite you to share your thoughts and ideas in the comments below, sparking a collaborative discussion that could drive future advancements. If this exploration of cyber-physical systems and data integration has sparked your interest, don't hesitate to dive deeper. Numerous resources are available online, from academic papers to industry reports. Stay informed, engage with experts, and contribute to the ongoing dialogue. Thank you for joining us on this journey. If you found this video insightful, please like, share, and subscribe for more explorations into the future of technology. And don't forget to hit the notification bell so you stay updated. Your support helps us continue bringing you content that matters. Let's work together to shape a future where cyber-physical systems enhance our lives responsibly and ethically.